A sampling distribution of a statistic is a probability distribution of a sample statistic, such as the mean or proportion, formed by taking all samples of size n from the population. So remember that a statistic is just a numerical measurement of a sample. So the sample mean, median, mode, standard deviation, those are all statistics. So for example, suppose we examine the population of full-time students enrolled at a college. The population may consist of thousands of students. We may be interested in their mean age, their mean height, their mean GPA, mean commute time, etc. The population of each will have a mean mu and a standard deviation sigma. If we take all possible samples of size n students, then each sample will have its own mean. So x bar sub 1 will be the mean of sample 1. X bar sub 2 will be the mean of sample 2. And x bar sub n will be the mean of sample n. If there are 4,000 students and we take samples of size n equals 10, then there are 4,000 to the 10th samples for which you would need to find the sample mean. And that's a lot of work. Now where that 4,000 to the 10th comes from is just the multiplication rule, that if you have 10 students that you're selecting, and there are 4,000 possibilities for each spot, you would have 4,000 times 4,000 times 4,000 10 times to get the total number of possibilities. Okay, so that's where 4,000 to the 10th comes from. The resulting distribution of all these sample means is called the sampling distribution of sample means, or SDSM for short. Okay, so sampling distribution of sample means, SDSM. We sample with replacement so we can treat the outcomes as independent and make the calculations easier. So that's what I was just mentioning with the 4,000 to the 10th. We're treating those as independent selections every time you choose a student. We're assuming you can choose the same student again for each of the spots, and that just makes it easier with the calculations. Okay, and similarly, we can create a sampling distribution of sample proportions by repeatedly taking n samples and calculating a sample proportion or percentage rather than a sample mean. So rather than taking samples of size 10 students and calculating their commute distance or their GPA, their mean GPAs or mean commute distance, we could look at the proportion of students who support a certain social issue. Okay, so rather than a sample mean, that would give you a proportion or percentage for each sample. Okay, so to give you an idea of what a sampling distribution of sample means is, there's an applet that I use, and you can see the URL up here at the top. If you go to Google and do a Google search for central limit theorem applet, you should be able to find something similar to this applet, okay, if not this applet itself. Okay, so we're given a normal distribution. Okay, it's called the parent population, so we're starting with that population. It has a mean of 16, a median of 16, and a standard deviation of 5. We're not going to pay attention in this class to the skew or kurtosis. We're just going to pay attention to the median and standard deviation. Okay, so we start with just a normal distribution, and notice down here it says distribution of means, okay, with n equals 5. Now I'm going to change that to n equals 2, just so we can go through a few of these and show you. And what it's going to calculate, it's going to find the mean of samples of size 2. So if I click animate, notice what's going to happen is out of that parent population, you're going to see 2 sample pieces of data drop out. So it's randomly choosing 2 pieces of data from that parent population. It's calculating the sample mean and plotting it on this axis down here. If I animate again, it's going to randomly choose another 2 and calculate the sample mean, and then plot it on the axis down here in blue. Okay, so if I do that several times, okay, so I'll do it again. There's another sample of size 2 in the sample mean. The 5, 10,000, 100,000, this is just an applet that allows you to do 5 at a time. And notice the repetition over here, reps 3. That means I've taken 3 samples of size 2, and the sample mean for those 3 samples is what is plotted down here. So if you were to label the axes, the original parent population, you would look at that as just x, like random variable x, and then the blue axis would be x bar. Okay, you would label this one with x bar because you're finding sample means. So if you look at the repetition, so far we've taken 3 samples of size 2 and calculated the sample mean. Okay, now if I click 5, it's just going to do 5 at a time. Okay, so now notice there are 8 repetitions, so it randomly chose 5 more samples of size 2, calculated the sample mean for each of those samples of size 2, and plotted them on the axes. Now if I do 10,000, once I click that, notice over in the reps, it's going to say 10,008. And there you can see, we end up getting a distribution that is more defined in its shape. It takes several repetitions in order to actually build the distribution of sample means, because you need to do several repetitions before it gets a shape. Okay? If I do 10,000 more, now I'm up to 20,000, 8 repetitions, 10,000 more, and so on. And you notice that after you do 20 or 30,000 repetitions, notice that it's not really changing shape much. Okay, but you'll notice that the frequency up the side here is changing. Okay, if I do 100,000, actually let me get this to, there's 100,008 repetitions. I think that's 100,000. If I do 100,000 more, well, now I'm up to 200,000, 100,000 more. So if I do that several times, I'll eventually get to like 1,000,000 repetitions, or samples of size 2. Okay, so there's about 1,000,000 samples of size 2. And we notice that the shape hasn't changed much after we got past about 30,000 repetitions. Okay, so this blue distribution down here is the sampling distribution of sample means, the SDSM. And what you might notice is that it's a little more narrow than the original parent population. And notice that the mean, 15.99, is very close to the mean of the original 16. Basically saying the center right here is the same center for both distributions, right about 16. Now notice the standard deviation, which measures how spread out the data is, or the variation in the data. Well, down here it's about 3.5, and in the original it was about 5. So that's just saying that the distribution of sample means, or the sampling distribution of sample means, is more narrow than the original. Okay, so those are samples of size 2. If I kick up the sample size to say, let's say 10, now if I animate, think about what's going to happen. Now instead of taking samples of size 2 and calculating the sample mean, it's going to take 10 values out of that parent population, calculate the sample mean of those 10. Okay, so every time I choose to animate, it's going to choose 10 out of that parent population and calculate the sample mean. Okay, and again, it's going to take many repetitions in order to get a shape down here for this sampling distribution of sample means. So if I do 5 several times, okay, now it's starting to build up a shape, right? Oops, I just said 10,000. Notice that made the shape that it's not really changing much from now. Okay, I keep hitting 10,000, so now I'm up to about 100,000 samples of size 10, and notice that the shape is now pretty much staying constant. The frequency is changing as I go, but the shape is staying the same. And what you might notice is the mean is still right about 16, but the standard deviation now is down to 1.58. So now that standard deviation is even smaller than it was for samples of size 2. Okay, so this sampling distribution of sample means is more narrow than the original distribution. Okay, now let me change that to a much larger, like 25. If I animate, think about what's going to happen. It's going to take 25 individual pieces out of that parent population, calculate the sample mean, and plot it down here on the axis in blue. Okay, if I do that one more time, just so you can see it again, it's going to randomly choose 25 more, calculate the sample mean and plot it. Okay, and then if I do that many times again, notice the shape isn't changing even though the frequency is. The shape is not changing. And what you might notice is that each of those, whether the sample size was 2, so whether n was 2, 10, or 25, notice that we have a symmetrical distribution down here. And you can actually do what they call fit normal on this applet. And you can see that a normal curve will kind of follow that distribution. Okay, the original was normal, and the sampling distribution of sample means is normal. And we'll get into what happens there in the next video. But I want you to get a basic understanding of what is meant by a sampling distribution of sample means. And again, all that is you're choosing a sample of size n, in this case 25, calculating the sample mean, and plotting it on a new distribution.